In this lecture on global games, we'll introduce a set of new assumptions about the information structure of economic agents that will allow us to understand better how coordination games work and how to predict the outcome of such coordination games. So coordination is very important in finance. We saw last week in the Diamond and Dybvig model that to understand bank runs and to understand the fragility of financial intermediation, it's very important to take into account coordination between bank depositors, in particular that the behavior of bank depositors involves strategic complementarities. That is, my incentives to take one specific action increases if I see that other agents are also taking the same action. For example, if I see that people are lining up to withdraw their savings from the bank, I also have an incentive to do the same thing. When figuring out what is my optimal action, I want to understand what other people are doing as well. So we saw an example with the run on a bank. There are several other examples. We'll study today also an attack on a currency, and also applications for rolling over corporate debt, especially short-term debt. So in the model of a Diamond and Dybvig, there are multiple equilibria. We saw that there were two Nash equilibria, one in which patient depositors would leave their money in the bank, and one in which patient depositors will withdraw their money from the bank. The problem is that we did not really understand when each equilibrium will occur. It was one or the other, but when would it be the case? It wasn't clear, right? So in terms of making predictions, that doesn't get us very far. We know that in principle, one thing can happen or the other, but we don't exactly know when we're going to observe a given equilibrium. So of course, with any model, we made strong assumptions, right? And so then the question becomes, if you relax this assumption, do you still obtain the same conclusions or very similar conclusions, or does it really change things when you incorporate more realistic features of the economic environment? So one such feature is that we assume that everyone has the same information. So everyone observed a public signal. So all information was public knowledge. So everyone knew the same thing. But of course, in reality, different people are going to observe slightly different things, are going to have at least slightly different information. And so global games take that into consideration by introducing private signals. And so this is the idea that each agent is going to know something at least a little bit different from other economic agents. And doing so, so having a more realistic information structure is not just for the sake of making the model more realistic, but more interestingly, it allows to identify a unique equilibrium, even though we have a coordination game with strategic complementarities. And what's really quite interesting is that in this case, the equilibrium outcome will depend on fundamentals, so on economic fundamentals. This reflects the fact that in practice, bank runs do not occur randomly. According to the Diamond and Dybvig model, for all we know, if we switch from one equilibrium to the next, that could be completely random. But in practice, of course, bank runs tend to occur in times of crisis. For example, during the Eurozone sovereign debt crisis in 2011, Greek banks were hit when fundamentals deteriorated. And so the way that global games help identify the unique equilibrium is quite clearly summarized by two pioneers in this literature, Morris and Shin, in the following quote. And so just saying that there were two very strong assumptions in models like those of Diamond and Dybvig. And the first one is that economic fundamentals were common knowledge. So everyone knows these fundamentals, and everyone knows that other economic agents know them as well. Second, when we studied equilibria, so remember, these were Nash equilibrium, so we took as given the behavior of other economic agents. So that implies that anyone knows what other agents will be doing in equilibrium. So there's no uncertainty about what anyone else is doing. So of course, we make such strong assumptions to have tractable models, but it also has a cost, because it implies that in this case, the beliefs and actions of agents can be perfectly coordinated. All agents know exactly the same thing, and they can perfectly coordinate their actions. And this is the concept of a Nash equilibrium. So if you use the global game methodology by modeling information in a more realistic way, by taking into account the fact that you don't necessarily observe what other people do and you have slightly different information, then you will be able to identify the unique equilibrium. Okay. So to do that, we have to take into account the fact that there's two types of uncertainty. The first one is so-called fundamental uncertainty. It is the uncertainty about economic fundamentals, about the state of the economy, about the state of a particular corporation, a particular bank, and so on. The second one is so-called strategic uncertainty. And this is uncertainty about the behavior of other economic agents. Now, why do we care about that? We care about that whenever there is a coordination problem in which my optimal action is going to depend on the actions taken by other economic agents. And so in this case, it becomes very relevant what they are doing. And so it becomes relevant whether I know or not what they are doing. So what we'll do is that we'll study the model of Goldstein and Posner. So it is an extension of the model of Diamond and Dybvig, but with a global games methodology. And we'll see how we'll be able to identify the unique equilibrium outcome and to relate it to economic fundamentals. So as in the model of Diamond and Dybvig, there's going to be a proportion lambda of impatient depositors who always withdraw, right? So we're only interested in the behavior of patient depositors who are going to meaningfully choose whether or not to withdraw their savings in the short term. But now we'll introduce some uncertainty. So instead of receiving R for sure, as long as the bank is not bankrupt in the second period, now patient depositors are going to only receive R with some probability, and with some probability P that is going to depend in theta, where theta are economic fundamentals. And so this is referred to as the state of the economy, but it can really reflect anything, the state of a particular bank or whatever you want it to be. And so you receive R with this probability P of theta, and you receive 0 otherwise. Okay, so it's a bit stylized, but really the important thing here is that the payoff you're going to receive if you invest for the long term, even if no one withdraws early, is going to be uncertain, first of all. And second, it's going to depend on some economic fundamentals. Okay, so what are the prior beliefs of agents? They believe that theta is uniformly distributed on 0, 1. So this is not crucial. What's going to be crucial, however, is that now each depositor is going to receive a different signal, and a signal which is informative, but imperfectly informative about theta. And this is the only thing they're going to observe. So furthermore, they are not going to observe what other people are doing. They will know that other people are going to receive signals, and depending on the signal that they themselves observe, they will be able to infer that other people observe something maybe a bit similar, even though they don't exactly know what the information of other people is. So what is a signal received by a depositor I? So it's denoted by theta I. It's going to be centered on the realization theta of the state of the economy, but it's going to be a noisy version of theta, right? So there's this noise terms epsilon I, which is uniformly distributed in this interval with this cumulative distribution function. Okay. And so each depositor is going to learn something about theta, but the larger epsilon is, the wider this interval is going to be. And so the less informative their signal is going to be. Okay, so what is the optimal strategy for patient depositors? We already know that impatient depositors are going to withdraw no matter what. So for patient depositors, when the signal realization is low enough, regardless of what other depositors are doing, they are always better off withdrawing early. And the idea here is that even if everyone rolls over, even if no one withdraws early, the probability P of theta of receiving R instead of 0 is going to be so low that they are better off withdrawing early. So the bank has terrible fundamentals. You should withdraw your savings as soon as possible. And this is a dominant strategy because it is optimal regardless of the actions of other people. Now, on the contrary, when the realizations of the signal theta I are high enough, then it is a dominant strategy to roll over. So no matter what other people are doing, the bank is doing so well, it's generating such high returns that you are better off rolling over your funding, not withdrawing early. And this is true regardless of what anyone else is doing. But now, of course, the interesting thing is what's going to happen in between these two extreme cases when the signal is very low and when the signal is very high. What we can show in this type of model, there's going to be a so-called threshold equilibrium in which patient depositors are going to withdraw their funding, they're going to engage in a bank run, if and only if their signal theta is below a threshold theta star. If theta I is above theta star, they're going to roll over their funding. You have two actions. You can either withdraw your funding or roll over your funding. And you observe one signal theta I. And so as you can see here, the larger theta I is going to be, the better your information about the state of the economy. And so the more optimistic you're going to be. And so here this is saying that if theta I is less than some threshold, you are going to withdraw your funding. And if theta I is above this threshold, you will be happy to roll over your funding. So it makes sense. Okay, so this is a threshold strategy for each patient depositors. You run if and only if your own signal is going to be below a threshold. And so this threshold is going to be the same for all depositors. But of course, this signal theta I will vary across depositors. Everyone will observe something a bit different. So now what is the proportion of depositors who will withdraw? So there's a continuum 0, 1 of depositors. There's always a fraction lambda who withdraw no matter what. These are the impatient depositors. And then among the fraction 1 minus lambda of patient depositors, only those that receive a signal below theta star are going to withdraw. And so this is going to be this proportion. And so it's a probability that theta I is less than theta star. So what is this probability? And in particular, we want to relate this probability to the economic fundamentals and the state of the economy, theta. So to calculate this probability, we're going to substitute for the expression for the signal in this expression. So theta I is equal to theta plus epsilon I. So this is what we have here. And now when we have an expression like this, we want to isolate the random variable. So here the random variable is epsilon I. We throw everything else on the other side of the inequality. And now we have the probability that epsilon I is less than something. But we know that epsilon I is distributed with this distribution function. And so the probability that epsilon I is less than something is simply the cumulative distribution function of this something. Okay. And so we know that this distribution function is increasing in its argument. Here we have minus theta. So we know that this whole thing, meaning this probability, is going to be decreasing in theta. And therefore, this whole expression here is going to be decreasing in theta, meaning that when economic fundamentals improve, there's going to be less agents who withdraw. More of them will be happy to roll over their funding. And on the contrary, when the economic fundamentals theta are really bad, then there's going to be a very high fraction of depositors who withdraw their savings. And so in this way, we can relate the equilibrium outcome. So whether there'll be a bank run, and more specifically, the extent, the magnitude of the bank run, we can relate that to the state of the economy, to economic fundamentals. And now we can engage in meaningful predictions, right? If you can predict what theta is going to be, you can start predicting what is going to be the magnitude of the bank run. And in particular, we can figure out state of the economy such that all patient depositors take the same action. So this is simply because in this case, the signal follows a uniform distribution, which is bounded. We know that this will be true for this distribution, right? When is this expression going to be equal to 0? So it's going to be equal to 0 whenever theta star minus theta will be less than minus epsilon. When is that the case? So let's find the minimum level of theta such that this is the case. So when is this equal to 0? We can just compare these two expressions. This will be equal to 0 whenever the argument is less than minus epsilon. Now remember that this function is increasing in its argument. And therefore, so we want to solve for theta. And so this is the case whenever theta is larger than this. So likewise, when will this function be equal to 1? And so when will everyone withdraw their funding? And we're going to figure out what is the maximum value of theta such that everyone withdraws their funding. And so we know that this function is equal to 1 when evaluated at epsilon or at any argument larger than epsilon, since this function is increasing. And so when is this equal to 1? Well, this would be equal to 1 whenever this is larger than that. And so this is the case. So when, again, this is larger than that, we rearrange for theta. And so we find that it's the case whenever theta is less than this threshold. Okay. So again, when theta is sufficiently low, so all agents are going to withdraw their funding. And when theta is sufficiently high, all agents are going to roll over their funding. And of course, in between these two extremes, there's going to be some proportion in between 0 and 1 of patient agents who are going to withdraw their funding. So here, this is a figure from the paper, and I'm going to focus on the top part of the figure. So here you have the proportion of agents who are going to withdraw their funding. And so when theta is sufficiently high, when theta is larger than this, it is this case. So this expression is equal to 0. And so this is equal to 0. And so who is going to withdraw is going to be a proportion only lambda of agents who withdraw. And this is the lambda you have here. Now, when theta is sufficiently low and theta is less than this, so now we are in this case, this expression here is equal to 1. And so this is equal to 1 as well, meaning that the proportion of agents who withdraw is equal to this, which is equal to 1. And this is a 1 you have there as well. Okay. And in between these two extremes, the proportion of agents who withdraw, as you can see, is linearly decreasing in the state of the economy. This is simply because of the assumed uniform distribution. With a normal distribution, you have something a bit more smooth, but the general prediction will remain the same, right? That the proportion of agents who withdraw is going to be decreasing in the state of the economy, theta. And so this type of model can really explain what happened in the financial crisis, for example, what happened to Lehman Brothers. So I will let you read a bit more, maybe even read this paper if you're interested in this. But the conclusion was simply that short-term creditors in investment banks, including Lehman Brothers, would tend to withdraw their funding during a crisis, which would precipitate bankruptcy. So in the second part of this lecture, we will study a slightly different model that is going to focus on a speculative attack on a currency in a fixed exchange rate regime. And so this is the original paper of Morris and Chin, which was seminal in the global games literature. Here we're simply going to follow a simplified version of this paper, as in the Tyrrell textbook. So we have a central bank that owns some foreign exchange reserves that it uses to defend the fixed exchange rate regime. And these foreign exchange reserves are worth theta. And the strategy of the central bank is simple. It's going to spend its reserve to defend the currency and to be able to buy the currency when other people are selling it, when speculators are selling it. And the currency is going to collapse if and only if investors collectively spend more than this amount theta. And so we'll denote by S, capital S, the total amount spent by speculators. And the currency is going to collapse if and only if the amount spent by speculators is greater than the central bank reserves. So speculators are atomistic. And so just one speculator like George Soros will not be enough to bring down the central bank. So it needs to be enough speculators who are going to attack the currency. And so each speculator has $1 to spend. And so we have a mass 1, so a continuum 0 amount of speculators, each with $1 to spend. So the maximum value of S is 1. And we'll see on the next slide what is the information of speculators on the value of theta. But they do not know the exact value of theta. To understand how the model works, at first you can assume that you know theta. So when would attacking a currency be a dominant strategy? Meaning that you are better off attacking the currency regardless of what other people are doing. So in this game, there are strategic complementarities. So for attacking to be a dominant strategy, we have to figure out when you're better off attacking when no one else is attacking. And so in this case, attacking will be a dominant strategy when theta is less than 0. So when is it a dominated strategy? Meaning that regardless of what everyone else is doing, you're better off not attacking. This would be the case when everyone is attacking. So S is equal to 1, and yet you are better off not attacking, meaning that the currency will not collapse. That would be the case even if when S is equal to 1, this is not verified, meaning that theta would be strictly greater than 1. So when theta is strictly greater than 1, regardless of what else is going to be, this inequality will never be satisfied. Okay, so let's be a bit more precise. So now we're going to specify what are the costs and benefits of attacking the currency. So attacking is going to cost C, which is in between 0 and 1, and the benefit is going to be 1. Speculator is going to compare the cost against the benefit. Also, the cost is going to be incurred no matter what. So even if the attack succeeds, you still have to pay the cost of attacking the currency. So each investor is going to receive some information on theta. It's going to receive some signal. We're going to study two different cases. At first, we're going to study the case with a public signal, meaning that all investors, all speculators are going to receive the same signal on theta. So this is a public signal, and we call that Y. And so this is a noisy version of theta. You can see that it is centered on theta, but so here you have this random variable eta with a cumulative distribution function f. Okay, so the signal Y will be informative about theta, but not fully revealing, not perfectly informative, because here sigma is positive. The second case we're going to study is the case of a private signal in which each individual investor is going to observe something a little bit different. So again, the private signals are centered on theta. So they are informative about theta, but they are imperfectly informative. As you can see, there's again this random variable, eta I. And so now this random variable is going to be different for every investor. So every investor is going to receive a different signal. And again, the magnitude of the noise of the signal is parameterized by sigma. The larger sigma is, the more noisy the signal is, so the less informative it is. And all these variables are IID, meaning that they are independent, so uncorrelated, and identically distributed. So they all follow the same distribution. For example, you can think about normal distribution with a mean of 0 and a variance of 1, because in any case, we have this parameter sigma here. Notice that signals don't need to be very different from one another. Now, they can be very precise. If sigma becomes very small, different signals observed by different economic agents will still be very similar. So you don't need people to have extremely different beliefs. Okay, let's start with a case of a public signal. So this case. Unsurprisingly, when all investors receive the same signal, we're going to see that there are multiple equilibria, meaning that for a given realization of a signal Y, often there's going to be different outcomes. And so we look for Nash equilibria, just like we did in the model of a Diamond-Dybvig. So first, we're going to look for a Nash equilibrium in which all investors do not attack. So if none of them attacks, S is going to be equal to 0. And if one atomistic investor deviates, S is still going to be approximately equal to 0. So how do we check this is a Nash equilibrium? So remember, a Nash equilibrium is a set of actions such that given the actions of all other players, it is not in the interest of any individual agent to deviate from his postulated action. So we're going to suppose that all other speculators indeed do not attack. And we're going to see if it is in the interest of anyone, any individual speculator, to deviate. So how do we rule out deviations? So deviations will be suboptimal, meaning that we will indeed have a Nash equilibrium if the payoff I get if I deviate and if I attack the currency, which would be equal to this, is less than what I get if I follow my postulated strategy, meaning if I do not attack. And so we will assess that given the action of other players, so given that S is equal to 0. Okay. So of course, if I do not attack, I get 0. I do not spend anything and I do not get any benefit. Now, if I attack the currencies, there's two possible outcomes. The first possible outcome is the attack will succeed, in which case I would have spent C, but I would have earned 1. The second case is the attack fails, in which case I will just have spent C and I would not have derived any benefit from it. So what is the probability for the attack to succeed? And this is here. So we know that the attack is going to succeed if and only if S is greater than theta. So what we want to do here is that we want to calculate the probability for S to be greater than theta, given that S is equal to 0. So the probability for S to be greater than theta, given that S is equal to 0, is equal to this. And also we take the conditional probability based on the information of economic agents. So it is conditional on their signal Y. Likewise, what is the probability for the attack to fail? So this is a probability for theta to be greater than S, with S equals to 0. And so this is equal to this probability. Again, this is a conditional probability, conditional on the information of economic agent, which is Y. Okay, so we have these two probabilities that we need to calculate. So how do we do that? So this is the probability of theta being less than 0. So the one you have here. So what we do is that we're going to use the expression for the signal and we're going to use this equality to replace theta by this expression. And now, because this is a probability conditional on Y, so Y will be treated as a constant here. So what is the random variable? It is theta. And so what we do is that we isolate the random variable and we write this expression as a probability that this random variable is greater than this amount. But we know that this random variable is distributed with this distribution function. And so this probability can simply be rewritten like this. Okay, so this is what we have right here. The sum of these two probabilities is equal to 1. So this probability is simply equal to this. Now we have twice this function f. So we'll be able to simplify the expression on the left-hand side. This is how we get to the third line. And now we want to solve this expression for y. So for which signals y is it indeed going to be an equilibrium that investors do not attack. And we find that this is an equilibrium as long as y, the signal they receive on theta, is sufficiently large. And so it makes sense. If they receive a pretty large signal on theta, they believe that the central bank has enough reserves so that the currency will not collapse as long as other investors do not attack. And so in this case, not attacking is indeed a Nash equilibrium. Let's look for another Nash equilibrium. And now this is going to be an equilibrium where everyone is going to attack. So if everyone attacks, S is equal to 1. Let's look for any potential deviations. So we want to make sure that if everyone else attacks, so if S is equal to 1, it is indeed in the interest of any individual speculator to attack as well. So if I don't attack, I get 0. If I do attack, I'm going to get this expected payoff. So with some probability, the attack is going to be successful. This is a probability that S is greater than theta. But here, I take the action of other investors as given. So S is equal to 1. So what is the probability that S is greater than theta? Is a probability that theta is less than 1. And again, I condition on my information, which is a public signal Y. If the attack is successful, again, I get this payoff. Plus, with some probabilities, the attack will be unsuccessful. That's whenever the central bank reserves theta are greater than S, where S is equal to 1. Conditional on my information, and my payoff is minus C. Okay. So again, we need to calculate this probability. We use the same techniques. What is the probability that theta is less than 1 conditional on my information? Again, I replace by this expression for the signal. And by substituting for theta, I find that this is equal to this probability. Again, my information is a signal, so I take y as given. I isolate the random variable, which is eta. And given that the distribution function of eta is f, I get that this probability is equal to z. I'm going to replace this probability by this expression. Then I simplify and I get this inequality. Again, I solve for y. I want to know for which values of the public signal y it will indeed be a Nash equilibrium for investors to attack the currency. And I find that this is the case whenever y is sufficiently low. Again, that makes sense. Remember that y is the public signal about theta. So when I believe, what everyone believes, it's not just me, it's a public signal. When everyone believes that the central bank does not have enough reserves to defend the currency when everyone attacks the currency, then it's going to be a Nash equilibrium for all investors to attack the currency. So now let's put these two Nash equilibria together. So the first one is an equilibrium where no one attacks the currency when y is greater than this. And this is what I'm having here, and no one attacks the currency, so S is equal to 0 whenever y is larger than this. So for any value of y here. The second Nash equilibrium is that everyone attacks the currency, so S equals 1 when y is less than this amount, and notice the plus 1. So this is larger than that. And so y is less than this, then it's a Nash equilibrium for everyone to attack the currency. So S is equal to 1. And so this is the case for any public signal here. And so it means that in this interval, there's two Nash equilibria. It is possible for everyone to attack the currency or for no one to attack the currency. And this is reflecting of strategic complementarities, the fact that investors can coordinate on not attacking, in which case the currency will not collapse, and it is indeed optimal for everyone to not attack. or everyone can attack, in which case the currency will collapse and it will indeed be optimal for anyone and everyone to attack. Okay, so this is very similar. What's happening here is very similar to what we had in the Diamond and Dybvig model. It's a coordination game with multiple possible outcomes. So again, this is not great because we cannot really predict what's going to happen in this interval. So now let's study the case with a private signal. So this is the case when each investor receives a signal yi on the value theta. And in this case, we'll be able to identify the unique equilibrium. So again, there's two actions. You can either attack the currency or not attack the currency. And we're going to postulate that each investor is going to attack the currency if the signal yi is sufficiently low. So it's below some threshold that we call y star. And it's going to not attack the currency if the signal is above y star. Okay. So supposing that everyone else follows this strategy, this threshold strategy, then what are the resources spent? And here we're going to write the resources spent on attacking the currency S as a function of theta. We want to relate the outcome. So all the actions taken by economic agents, we want to relate the outcome to the economic fundamentals. With a continuum of depositors, each with $1 to spend, the total resources spent will be equal to the probability that each investor is going to attack the currency. When that's the case, so you attack whenever your signal yi is below y star. So what is the probability that yi is less than y star? Conditional on theta. So again, what we do is that we replace yi by this expression. And we find that this probability is equal to this. So this is equal to yi. Now, as always, so we isolate the random variable, which is eta I. We use the distribution function of eta I, which is f, to rewrite this expression like this. Okay, so here we have that the total quantity of resources spent given fundamental theta is equal to this. And again, unsurprisingly, we find that the higher theta is, the lower the resources spent on attacking the currency is going to be, because the CDF is increasing in its argument. So the condition for the currency to collapse, as before, is when the resources spent, S, are greater than theta. And so here's the only difference, is that we relate the resources spent to the economic fundamentals, or to the value of theta. How to rewrite this inequality, this condition for the currency to collapse? We can just throw everything on the left-hand side. And this is the case whenever S minus theta is positive. But now what is the behavior of this function? As just discussed, S of theta is decreasing in theta. Now this is what we have here. And obviously minus theta is decreasing in theta, meaning that the left-hand side of this equation is decreasing in theta. And the currency is going to collapse whenever this expression on the left-hand side is positive. So this means that as long as theta is sufficiently low, the currency is going to collapse. And so the currency is going to collapse if and only if theta is less than a threshold that we call theta star, that is such that this expression is equal to 0. So this expression is equal to 0 at theta star. And so rewriting using this expression for S of theta, the condition that implicitly defines theta star is this one. Okay, so here you have the function S of theta minus theta. We don't exactly know what it looks like. It doesn't really matter. What really matters is that it is decreasing in theta. And so there's going to be a value theta star here. So this is theta star, such that this function is positive whenever theta is less than theta star. So for any theta here, and when this function is positive, so what does this mean? It means that the currency collapses. Okay, and when this function is negative, So for any theta greater than theta star, the currency is not going to collapse whenever this function here is below 0. Okay, so now what we would like to know is, what is this theta star? What is this threshold value of fundamental such that the currency is going to collapse if the reserves of the central bank are below theta star? So to derive theta star, we have to consider now the problem of each individual investor. So given a signal yi, so this is the information of each investor, this investor is going to attack the currency if and only if he's better off doing so. He's better off doing so if and only if the expected payoff he gets if he attacks is greater than what he gets if he does not attack, which is 0. If he attacks, now we know that the currency is going to collapse if and only if S is greater than theta. But now we also know that the currency is going to collapse if and only if theta is less than theta star. And so now we're going to use this condition. And so this is a probability with which the currency will collapse. And so from the perspective of individual I, we're going to condition on this information, the signal yi. And so the currency is going to collapse with this probability. In which case, the payoff if I attack will be equal to this. And the currency will not collapse with that probability, in which case the payoff I get if I attack is equal to that. So what is the threshold y star such that the investor will be indifferent between attacking and not attacking? So y star will be the value of yi such that this expression here is equal to 0, such that I'm indifferent between attacking and not attacking. So I just rewrite this expression with yi equal to y star. And by definition of y star, the expected payoff I get when I attack will be equal to the payoff I get when I do not attack, which is 0. So I get this expression that defines y star. Again, I have this probability. So now we know how to solve this, right? We replace, so we use this expression. So here is going to be evaluated at y star. And so theta can be rewritten like this. We isolate the random variable eta. And we use its cumulative distribution function f to get this expression for this probability. And we rearrange, we get this expression. And now finally, if you compare this equation, notice especially the left-hand side, to that equation. Notice the left-hand side again, which are the same. So we can equate these two equations. And we find that theta star is equal to 1 minus c. Now this is what we have right here. Okay. And so now we know exactly. So if we go back to the previous graph, so this is theta star, and the currency will collapse for any theta less than theta star, and it will not collapse for any theta greater than theta star. And now we know what the value of theta star is. So now if you're the central bank governor and you know what your foreign exchange reserves are, and you know roughly this type of signals that investors are going to receive, even though there's some uncertainty about the action taken by any individual investor, you know in the aggregate what they will do. And so you know if the attack on the currency is going to succeed or not. And so again, this is pretty nice because now you can really relate the equilibrium outcome to the fundamentals, even though there is a coordination game with strategic complementarities. So in terms of prediction, this is much better to a model with a public signal in which there was a range of signals for which you did not know what the outcome would be. So you can also use this theory from a corporate finance perspective. This can explain why borrowers can be fundamentally solvent, meaning that they will be able to reimburse their debt if they could refinance their debt in the short term. And they will ultimately be able to reimburse their debt in the long term, but they may face some illiquidity in the short term. And so short-term illiquidity is when your creditors refuse to refinance or roll over your funding. And so this is why whenever a firm is facing illiquidity, whenever a firm is distressed, what's really important is to coordinate the interests of creators. So for example, Morris and Chen here mentioned the creation of a creator pool such that creators will hopefully coordinate on the best outcome from their perspective, which would be that all of them roll over their funding. You want to avoid a coordination failure in which all creators are going to withdraw their funding from the firm. That would precipitate a bankruptcy that could otherwise have been avoided.